This will be my quiz solutions for quiz 8, spring 2023. So the first question, you have pole zero plots for transfer functions H1, H2, and H3. And part A asks, is filter 1 best described by a low pass, high pass, band pass, or stop band filter? Briefly describe why. I'll basically just draw it schematically, but you should probably do it differently. Basically, there's going to be zeros at these earlier frequencies right here. So this is from negative pi over 2 to pi over 2. And beyond that, it's going to increase, but it's also going to decrease when you hit the moment that you get to pi. So what this will look like, if you draw it, is going to look like this. And where is it going to centrally peak at? This will be at 3 pi over 4. And if we draw the symmetrical end, that's at negative 3 pi over 4. If you want to draw this a bit better, for example, in between zeros, it's going to look like it's going to go up just a bit, just a smaller peak. Then this is kind of what you expect to get if you drew it a little bit more proper. This is 3 pi over 4, negative 3 pi over 4, and you would realize the answer is a bandpass. So you just need some response that says that it allows frequencies near central frequency of 3 pi over 4 and negates the rest. Next is FIR2 an FIR filter or an IR filter? Briefly describe why. And without even talking about filter 2, basically you'll need to know that FIR filter, it is an FIR filter if there's a pole not at the origin. And why does it matter about what's the deal about this? If you remember an FIR filter, it has some form like some coefficient AZ to the negative 1 plus BZ to the negative 2. Let's imagine it's like this, whatever degree polynomial you want. And basically, let's say you multiply this by Z squared or Z squared, you'll see that at most it'll have a pole at the origin, and that's it. This is actually a causal FIR filter. If for some reason you want to explore beyond what this actually means, there's one extra case for an anti-causal filter, which takes the form like AZ to the first power plus BZ squared. Its pole is actually going to be at infinity. So there's really two cases for an FIR filter. One where its pole is at the origin and one where it's at infinity. If there's a pole anywhere else, it's an IIR filter. And that's really it. So to answer the actual question, is FIR a filter an FIR IIR? You just look at this filter 2 right here, and obviously it's an IR filter. There's so many zeros, not so many poles throughout the whole thing. Next question. For filter 3, identify the transfer function h of z. Okay. So you're just going to look at these zeros that you get. There's 3 of them, so you expect a third degree polynomial and z to negative 1. So h of z equals 1 minus 0.5 z to negative 1. Let's do the top one now. 1 minus j z to the negative 1, and then the bottom one, 1 plus j z to the negative 1. If you're worried about this pole, for example, then you'll realize it's actually already built into this answer, because if you interpret it as multiplying this by z cubed over z cubed, then this takes care of the pole. So you're good to go. Did I mess up? No, yeah. So filter 3 is an FIR filter, yeah. Okay. Next. Identify which filter's pole zero plot matches with each magnitude response below. So let me zoom out real quick for this one. And let's say I wanted to start with filter 1. Okay. And I want to match which one? I'm looking for zeros at 0, pi over 4, pi over 2, negative pi over 4, and pi over 2, negative pi over 2. And it's going to be obviously this one right here. So this is filter 1. Let's say I want to do filter 2 now. Which one does that match to? First of all, you can look at the zeros, but first I'm going to say, hey, this is actually going to be a low pass filter. It's going to high magnitude at low frequencies, and it's going to dip to 0 at 3 pi over 4. You're going to realize this one pretty quickly. Filter 2. And by process of elimination, it's obviously magnitude response A corresponds to filter 3. But let's just talk about, let's just pretend you didn't know that and you want to explore further. This is going to be a high pass filter. Okay, that's what you get when you see this part, obviously. And it's going to be a high pass beyond pi over 2, where pi over 2 and negative pi over 2. Something additional to note is this 0 here, this 0 at the 0.5 is not in the unit circle. So that's why its magnitude response is not actually at 0 at the 0. Otherwise, the frequencies at pi over 2 and negative pi over 2, it's 0. It's actually on the unit circle, and that's why you get an exact 0 magnitude response reflected into its answer. So just a little bit of intuition of visualization. Next, question 2. Oh, I went too far. Let's why is it doing this? Okay. Determine the impulse response age event for a filter defined by this. H is 0.5 n cosine pi over 0.5 pi n u event. So to determine the Z-transform, you need to go to the table. So just go down. So let's just see this. You go down the list and you realize it's this one right here. So let's just go back. Let's hope I get this right. Let's say I want to do this term right here, and I'm going to see that this second term here is actually very similar, but it actually has a time delay. So let's just do the first term because I don't have so much space to write. It would be 1 minus, let's say your parameters are, let's say, A equals 0.5 and omega naught equals pi over 2 or 0.5 pi. So 1 minus A z to negative 1, 0.5 z to negative 1 cosine of pi over 2, and it'll get 1 minus 2 times 0.5 z to negative 1 cosine of pi over 2 plus A squared, 0.5 squared, so 0.25 z to the negative 2. What you're going to realize here is cosine of pi over 2 is actually 0. So it simplifies a lot to 1 minus 1 plus 0.25 z to the negative 2. Now, to go to the second term right here, it's going to be similar to the first term, but it has a time delay of 2, which, how do you get, what's going to happen? You're going to get an extra factor of 0 to the negative 2 in the answer. So you get z to the negative 2 over 1 plus 0.25 z to the negative 2. Let's say you didn't know that, for example, how do you, where do you get the time shifting property from? You'll get it from this at the table of Z-transform properties. So right here, and it says take the Z-transform naturally and then multiply by z to the negative 2, which is the same amount and naught. Okay, and you just get the like terms, what do you call it? Simplify it. 1 minus z to the negative 2 plus 1 plus 0.25 z to the negative 2. And that's my answer. Next, is this filter FIR IIR? Briefly describe why. So like I said before, it's IIR if there's a pole not at the origin. And obviously, no matter how you think about it, there's a pole not at the origin here. So it's IIR. Part C, is the filter best described by a low pass, high pass, band pass, or stop band filter? Briefly describe why. So how I would probably go about this, I want to draw the pole zero plot and imagine what it looks like. So if I want to factor the above, I'll get 1 minus z, 1 plus z, 1 plus, let's say 0.5 j z, negative 1, 1 minus 0.5 j z to negative 1. I believe that's right. And let's say we draw this, it's going to have a 0 at plus minus 1. I'm going to draw the circle. And at, let's say, plus minus 0.5 j, you're going to have poles. If you draw this out in your mind of what this is going to look like, near the frequencies z equals 0 and pi, it's going to go to 0 magnitude, and near frequencies of pi over 2 and negative pi over 2, it's going to spike up from the pole. So this is pi over 2, negative pi over 2, and that is a bandpass filter. Next, the system is stable. Briefly describe why, true or false. So remember, it's stable if any pole, no, all poles, their magnitude is less than 1, and unstable if any pole is greater than 1. Your poles are inside the unit circle. So 0.5 and negative 0.5 j. So your answer is actually stable. It's true. It's true. The system is stable. And that'll be all.